Hi guys, today we shall be looking at balancing of Redox equation. How do we balance Redox equation? Redox equation is either balanced in simple medium or in complex medium. We recognize question that should be balanced in simple medium or in complex medium with the presence of oxygen. Take for instance, sodium plus copper to give copper 2 plus sodium. The state here is solid, this is aqueous, this is solid, and this is aqueous. Now you observe that for every reactant species in this equation given, there is no presence of oxygen. So it means that this equation can only be balanced using simple medium. But if I have a question that should be balanced in complex medium, one of the reactant species is going to carry an oxygen atom. For today, I will be teaching you how to balance Redox equation in acidic and alkaline medium using the half-cell equation method. So to operate the half-cell equation method, note that it is important to be acquainted with the following rules which serve as a guide to balancing of Redox equation. Now, the first one is the addition of oxygen to a substance or the removal of oxygen from a substance. And the next is the removal of hydrogen from a substance. The last one I'll be taking is the definition of redox based on electron transfer of electron. So let's try to navigate these three rules and see how it works. Before that, note that the half-cell equation method is subdivided into two. One, the oxidation method and the ion electron method. The oxidation method is the same thing as the use of oxidation number to balance half-cell equation, whether acidic or alkaline equation. So let's try this out. The question says, using the ion electron method and the oxidation number method, balance the below equation for a reaction occurring in an acidic medium, which means we are required to balance in an acidic medium. More so, we are required to balance in the two half-cell equation method, which is the ion electron method and the oxidation number method. To solve this equation, the first thing to do is to divide the given equation into two half-cell equations, the oxidation half and the reduction half-cell equation, as it implies a redox. While doing that, take note of the target elements in the given equation at the reactant side and at the product side. We have here manganese in its combined state with oxygen at the reactant side, and at the product side we have manganese in its free states. So these two chemical species can be made a half-cell equation. So we don't know yet whether it is oxidation half-cell equation or reduction half-cell equation. But what you are required to do is to match up this chemical species as a half-cell equation. So we have MnO4 to Mn2 plus. This is one of my half-cell equation, but I'm yet to know if it is going to be oxidation half-cell equation or reduction half-cell equation. So let's determine that. Recall that I mentioned previously that there are three rules of determining whether your half-cell equation is going to be the oxidation half-cell equation or reduction half-cell equation. One, addition of oxygen, removal of hydrogen, and electron transfer. But since we don't have hydrogen atom in the present example, we don't need this. Hence, we shall be working with whether addition of oxygen or with electron transfer. To determine that by using the addition of oxygen or removal of oxygen from a substance rule, let's look at this chemical species. You observe that manganese is in its combined state with oxygen here, while at the product side, it is in its free state without oxygen, which means that manganese has lost 4 atoms of oxygen to form its free state. And when oxygen is removed from a substance, the process is known as reduction. Hence, we can say that this half-cell equation is reduction half-cell. We can also determine this by the use of the oxidation number of the target elements, which is manganese. So what's the oxidation number of manganese in the combined state? To do that, equate MnO4 to its overall charge. So we have MnO4 to be equals to -1. Then, since we are determining the oxidation state of manganese, manganese will remain unchanged. So we have plus 4 atoms of oxygen. So I'm putting this into brackets so that it won't look like 40 equals to -1. So the oxidation state of oxygen is -2. So I have Mn plus 4 into bracket of -2 to be equals to -1. So in the end, I have manganese to be equals to -1 plus 8, which gives us +7. This means that manganese has moved from +7 to 2 plus. So what does this tell us? When we use these two values, that is the +7 and +2, to determine whether it is oxidation or reduction half-cell equation. So to determine this, we shall employ the number line method. On the number line, we have two kinds of movement. We have movement towards the right, which means loss of electrons, and loss of electron denotes oxidation. And we have this left movement, which means gain of electron, and this denotes reduction. So we can simply write that movement towards the right means oxidation or loss of electron, and movement towards the left means reduction or gain of electrons. So manganese moving from +7 to +2, we'll have our starting point to be +7, so we're going towards plus 2. 1, 2, 3, 4, and 5. Note that our movement is towards the left, which denotes reduction. That confirms that that's the reduction half cell. So how many electrons has manganese gained from plus 7 to plus 2? It means manganese has gained 7 minus 2, that's plus 5. It has gained 5 electrons in total. So moving forward to the next half cell equation, we have tin 2 plus to be matched up with its similar chemical species, tin 4 plus. So I have SN 2 plus aqueous to give SN 4 plus, still in its aqueous state. So this should be oxidation half. Since I have the reduction half here, but let's confirm that using the number line technique. Recall that when we move towards the right, it denotes loss of electron, which means oxidation. And towards the left means gain of electron, which means reduction. So we have tin moving from plus 2 to plus 4. So our starting point is plus 2 moving towards plus 4. So we have 1, 2, which means that tin has lost 2 electrons by saying 4 minus 2. That's going to be 2 electrons. Don't forget we moved from left hand side to right hand side. Hence we can boldly write that this half cell is oxidation half cell. Having divided the given equation into 2 half cell equations, we then try to balance the half cell equations atomically and then ionically. So working with the reduction half cell equation first, I have Mn O4 minus to give Mn 2 plus. Note that we are to balance atomically first before balancing ionically. Balancing atomically means to ensure that the same elements appear both at the reactant side and at the product side. Aside from that, to ensure that the number of atoms of those elements are equal for both the reactant side and product side. So looking at the reactant side, you observe that we have oxygen atoms here, but at the product side, no oxygen atoms. So we are expected to introduce 4 atoms of oxygen to the product side. And how can we get that? We'll get that through water, H2O. And don't forget, we are to introduce 4 atoms of oxygen. Of course, we now have 4 atoms of oxygen, but by implication, we are also having an introduced chemical species, which is hydrogen, and it has increased to 8 atoms of hydrogen. So here, we have 8 atoms of hydrogen, which means that the product side has hydrogen atom, but the reactant side does not have hydrogen atom. So can we easily introduce hydrogen atom to the reactant side by saying we have plus hydrogen ion. So how many hydrogen ion are we adding to it? We are having 8 hydrogen ion because we have 8 atoms of hydrogen appearing here too. Now let's check if the atoms are correct. We have 1 atom of manganese, and here we also have 1 atom of manganese. Note that counting the number of manganese present, you are to pretend as if this 2 plus does not exist. Also, we have 4 atoms of oxygen, and here too we have 4 atoms of oxygen, because this is invisibly 1, and hence we have 4 times 1, which gives us 4 atoms of oxygen, right? And lastly, we have 8 atoms of hydrogen, and this makes it 8 atoms of hydrogen because we have 4 times the subscript, which gives us 8 atoms of hydrogen. At this stage, you now know that the number of atoms of each element at the reactant side is equals to that of the product side. Hence, this task has been achieved. So we have to move to the next, which is to balance ionically. Here we deal with the overall charge of the radical and not the individual charges as we have here for manganese. And so note that the overall charge, which is -1 here, is usually multiplied by the coefficient of the radical. So we have 1 times -1. That will give us -1. And for the 8 moles of hydrogen atom, the charge, which is +1, is multiplied by 8, and that gives us +8. The total charge gives us +7. And to the product side, we have the charge of Mn to be 2 plus, multiplied by the invisible 1, so we have +2. And for the 4 moles of water, water has no charge, hence the charge is 0. 0 times 4 will give us 0. So the total value here will give us +2. Now, what is the difference between +7 and +2? The difference is 7 minus 2, which is 5. We now know that the charge at the reactant side is not equal to that of the product side. So the total charge here is plus 7, while the total charge here is plus 2, with a difference of 5. So what we have to do is to either reduce the charge of the reactant side to match up with plus 2 as it is at the product side, or to increase the charge at the product side by plus 5 to increase it to plus 7 as it is at the reactant side. Note that you either reduce plus 7 to plus 2 or increase plus 2 to plus 7. So for this example, I would like to increase the value from plus 2 to plus 7 as it is at the reactant side. Hence, I have plus 5 electrons. Now, there is a question around the addition of the 5 electrons. Note that the E minus here is a constant for the symbol of electron, and on no condition should it be changed to E plus. When you change it to E plus, what you mean is a positron and not an electron. Now, recall that to account for whether this is plus 5 electrons, we multiply the charge by the coefficient of the electron. Hence, we have minus 1, which is the charge of the electron, times plus 5, which is the coefficient of the electron, and that gives us minus 5. That means that you have just subtracted 5 from the number of electrons, and plus 2 minus 5 won't give you plus 7. So what are you to do? Just change the positive sign here to a negative sign. Note that you cannot tamper with this sign here because it's a constant. So by the time you multiply this by the coefficient, you have minus 1 times minus 5 instead, and that will give you positive 5, which means that you have successfully added 5 electrons. In a nutshell, we've been able to increase the value from plus 2 to plus 7. So plus 2 plus 0 plus 5 gives us plus 7. And by that, we've successfully balanced the reduction half cell equation atomically and ionically. Hence, this will become our equation 1. Now, moving on to the second equation, we have 10(2) plus to give 10(4) plus aqueous. Don't forget this in aqueous state, this liquid, this aqueous. Now let's balance atomically. We don't need to balance atomically because atomically both the reactant and the product sides are equal. Hence, let's balance ionically. Ionically, we have invisible 1 here multiplied by 2, which is the charge of the SN. So we have 2 plus, then we have plus 4 multiplied by the coefficient here, we have plus 4. It means that we can either increase this to plus 4 or decrease this to plus 2 so as to match up with the reactant side, or we increase this to plus 4 so as to match up the product side. This time around, I would like to increase this to plus 4 by the addition of 2 electrons. But don't forget, if it is written as plus 2E minus, it denotes that plus 2 times minus 1, and that will give us minus 2, which means we've subtracted 2 electrons instead of adding 2 electrons. So what we just have to do is to change the sign here to minus. By that doing, we have minus 1 times minus 2. That will give us plus 2, which means we have added 2 electrons. Plus 2. So plus 2 plus 2 will give us plus 4. It means that the ion at the reactant side is now equals to that of the product side. We have been able to balance atomically and ionically. So this becomes my equation 2. Having done that, the next is to equalize the coefficient of the electrons. That is, you have to make the coefficient of the electron in equation 1 to be equal to that of the coefficient of electron in equation 2. To do that, multiply equation 1 by the coefficient of electron in equation 2. So it means we'll have times 2, and equation 2 by the coefficient of electron in equation 1. And that will be times 5. And so we have 2 multiplied by MnO4 minus gives us 2 moles of MnO4 minus the same 2 multiplied by 8 moles of hydrogen ion will give us plus 16 moles of hydrogen ion. And for the product side, 2 is multiplied by this. We have 2 moles of manganese ion plus 8 moles of H2O. Then lastly, the electron. So we have minus 10 moles of electron. This gives us equation 3. Then moving on to the next equation, we have to multiply the whole of this by 5. And so we have 5 moles of 10(2) plus minus 10 moles of electron, and at the product side we have this multiplied by 5. Hence we have 5 moles of SN4 plus. This gives us equation 4. The next step is to add equation 3 to equation 4 to get the next equation. This is the major thing. Getting the next equation is the same thing as getting the total equation. So for the reactant side of equation 3 and equation 4, we have to add up the reactant side of equation 3 to that of equation 4. Hence we have 2 moles of MnO4 minus plus 16 H plus the next 5 moles of SN2 plus minus 10 electrons. So for the product side, we have the species at the product side for equation 3 to be added to that of equation 4. Hence, we have 2 moles of Mn2 plus 8 moles of H2O minus 10 moles of electron plus 5 moles of tin4 plus. Now let's check out for what can be cancelled. If this electron is transferred from the reactant side to the product side, the sign will change to plus 10E minus, and hence these two can cancel out. So it will be safe to cancel both electrons. Note that we cannot cancel out the 5 moles of Sn here against this. Why? Because the charges are different. Hence our next equation will be 2MnO4 minus plus 16 moles of H plus 5 moles of SN2 plus to give 2 moles of Mn2 plus 8 moles of H2O plus 5 moles of SN4 plus. To check your answer, we have 2 atoms of manganese here. At the product side, we have 2 atoms of manganese. At the reactant side for oxygen, we have 8 atoms of oxygen because the substrate is multiplied by the coefficient. Hence, I have 8. For oxygen at the product side, invisible 1 here, multiplied by 8, we have 8 atoms. For hydrogen, we have 16 atoms of hydrogen. And at the product side, we have 8 times 2 gives us 16. For tin, we have 5 atoms of tin. And at the product side, we have 5 atoms of tin. Atomically, it is balanced. Check ionically too. Ionically, we have minus 1 times 2, that gives us minus 2. Plus 1 times 16, that gives us 16 plus 16. Plus 2 times 5, that gives us plus 10. At the product side, we have plus 2 times 2, that gives us plus 4. This has no charge, so we have 0. 0 times 8, that gives us 0. For Sn, we have 4 times 5, that gives us plus 20. Gives us plus 24, and this gives us plus 24. Hence, it is ionically balanced. Now, we've been able to balance the redox equation using ion electron method. So the next method we are required to use is the oxidation number method. So how do we go about that? Divide the equation into 2 half-cell equations, that is the reduction half-cell equation and the oxidation half-cell equation. Then pretend as if you're not seeing the oxygen atom. So it means you're balancing only ionically and not atomically. The difference between ion electron method and oxidation method is that the ion electron method is balanced without checking if the number of atoms or the right element appear at both the reactant and at the product side. Hence, we have to balance ionically only. So for the first half cell equation, to balance ionically, we have to make use of the individual charge of the target element, which is manganese, because we pretended that the 4 atoms of oxygen does not exist. Hence, we cannot use the overall charge to balance it ionically. From our previous example, we know that the charge of manganese in this radical is plus 7. So we have plus 7 and here we have plus 2. So to make the ions of the 2 sides, that is the product and the reactant side, to be equal, we have to increase the number of electrons here to plus 7 by the addition of 5 electrons. Hence, we have plus 5 and this 2 gives us plus 7. It means that the charge at the product side is equal to that of the reactant side. This becomes our equation 1. So moving to the next equation, we have Sn2 plus aqueous. Don't forget the state of this is aqueous and this also is aqueous, to give Sn4 plus aqueous. The charge here is plus 2 and the charge here is plus 4. So I'm bringing this to plus 4. Hence, I have to add 2 electrons. I have plus 2 here because minus times minus gives you plus 2. So the total charge for reactant side is plus 4 and this is equal to the charge here. This equation becomes our equation 2. So the next step is to equalize the coefficient of the electrons. So to do that, multiply equation 1 by the coefficient of electrons in equation 2, and that will be times 2. And then equation 2 by the coefficient of electron in equation 1, and that will be multiplied by 5. Note that the value we are using to multiply applies to all the chemical species for that equation. Hence, we have 2 times MnO4 will give us 2 moles of MnO4 minus to give 2 moles of Mn2 plus. 2 times 5 gives us 10 electrons. This becomes my equation 3. For the second part of the equation, it should be multiplied by 5. So we have 5 moles of Sn2 plus minus 2 times 5 gives us 10 electrons to give 5 moles of Sn4 plus. This becomes our equation 4. Then the next thing is to get the net equation. So add equation 3 to 4 to get the net equation. So we are considering 2 MnO4 and 5 Sn2 plus minus 10 electrons for our reactant side. O4 minus plus 5 Sn2 plus minus 10 electrons to give the product side is this for the 2. So we have 2Mn2 plus minus 10 electrons plus 5 Sn4 plus. Note that we can easily cancel these 2 electrons. Hence, we'll be left with 2MnO4 minus plus 5 moles of Sn2 plus to give 2 moles of Mn2 plus 5 moles of Sn4 plus. Now, this is the last stage. At the last stage, we try to balance atomically. Now, when you look at the reactant side, you observe we have oxygen, but at the product side, we don't have oxygen. Hence, we can introduce oxygen to the product side by the addition of H2O. Now, the question is, how many atoms of oxygen do we need? We need 4 atoms of oxygen. Now, you cannot change the invisible 1 here to 4 because it is against the rule of chemical equation. So what do? You change this to 4 mole. Hence, by implication, you're having 4 atoms of oxygen because you have invisible 1 here. So 4 times 1 gives you 4. And then you have also introduced hydrogen and you have 8 atoms of hydrogen because you're going to have 4 times 2. Now, if you check it out, you observe that we now have oxygen atom here. We have oxygen atom also at the reactant side. But at the reactant side, we don't have hydrogen atoms. Hence, we are going to introduce hydrogen atom. Now, how many atoms of hydrogen? We have 8 atoms of hydrogen because we also have 8 atoms of hydrogen here. So all of this need not to reflect at the stage. So let's quickly add it up. I have 2 MnO4 minus plus 5 Sn2 plus 8 atoms of hydrogen to give 2 Mn2 plus 5 Sn4 plus and the 4 moles of water. Check your answer if it is balanced atomically and ionically. Our next question says balance the equation for a reaction occurring in acidic medium using ion electron method. So we have Cr2O7 2 minus plus SO2 to give Cr3 plus SO4 2 minus. And the following steps are to be followed. Number 1, divide the equation into 2 half cell equation. Then the next is to balance atomically and ionically. Thereafter, equalize the coefficient of the electron and sum up your equation to get the next equation. So the first is to divide the given equation into 2 half cell equations. Take note of the target atom, which is chromium. We have Cr2O7 2 minus to give Cr3 plus, this is aqueous. Then oxygen is present at the reactant side but not at the product side. It means that oxygen has been lost, and removal of oxygen from a substance means reduction. So this is my reduction half cell. To further confirm that, calculate the oxidation number of chromium in Cr2O7 2 minus. To do that, equate Cr2O7 to its charge, which is equals to -2. Since we are determining the oxidation state of chromium, which is Cr2, remains unchanged. 2 atoms of chromium plus 7 atoms of oxygen to be equals to -2. Recall that the oxidation state of oxygen is -2. Hence, we have this to be equals to -2. In the end, we have 2 chromium atom to be equals to -2 plus 14, which will give us +12. Divide both sides by 2. Then chromium will be equals to +6. It means that the oxidation state of chromium here is +6. Then the number line technique can be applied. Don't forget, as we move towards this side on the number line, we are moving towards loss of electron, which means oxidation. And then towards the left means gain of electron, which means reduction. Don't forget that chromium has moved from +6, which is here, to +3, which means that we have to move towards the left. So we have 1, 2, and 3. This means that chromium has gained 3 electrons in total from this place to this. That's 6 minus 3, which is equals to 3. And we have moved towards the negative direction. Hence, it is the gain of electron or reduction. That confirms this reduction half cell. So the next thing is to consider the second half of the equation, which is SO2 gas and SO4 2 minus. So we have SO2 to give SO4 2 minus in its aqueous form. Automatically I know that this is going to be my oxidation half. To check that out, determine the oxidation state of sulfur, and that should be +4, and the oxidation state of sulfur at the product side should be +6, which means that sulfur has lost 2 electrons, and loss of electron is oxidation. So the next is to balance the two half cell equation atomically and ionically. Considering the reduction half cell equation first, so we have Cr2O7 2 minus to give Cr3 plus. Note that there are 2 atoms of chromium here, and here we have 1 atom of chromium. So we have to increase the coefficient of this to 2. And the next is to consider that we have 7 atoms of oxygen at the reactant side, but no atoms of oxygen here. So what we have to do is to introduce H2O and then balance it up to have 7 atoms of oxygen, since we have invisible 1. So, and we have 7 times 1 to give us 7. But by implication, we have also introduced about 14 atoms of hydrogen, but no hydrogen atom at the reactant side. Hence, we have to introduce hydrogen ion. And how many atoms of hydrogen ion? We have 14 atoms of hydrogen ion, so that the number of hydrogen ion we have here can correspond to this. In a more broader view, what you're trying to do is you're trying to balance these two to become water, which is H2O. And when you add 7 here, you're going to get 14 atoms of hydrogen and 7 atoms of oxygen. So let's check if the number of atoms present at the product side is equal to that present at the reactant side. For the reactant side, 2 atoms of chromium and 7 atoms of oxygen, and then we have 14 atoms of hydrogen. At the product side, we have 2 atoms of chromium. Here, you have to pretend as if this charge does not exist. And 7 atoms of oxygen. Then we have 7 times 2 here, which will give us 14 atoms of hydrogen. With that, we've been able to balance the reduction half cell equation atomically. And now we have to balance ionically. To balance ionically, multiply the charge of the radical by its coefficient. That will give us -2, and this is +1 times 14, that gives us +14, and here we have +3 times 2, that gives us +6. For H2O has no charge, hence the charge is 0. 0 times 7 gives us 0. In the end, we have +12, and this gives us +6. Now, to equate the electron, we can either reduce this to +6 or increase this to +12. This time around, I would like to reduce this to +6. Hence, we'll have +6, and then this area too will be +6. So to do that, I am subtracting 6 electrons from the reactant side. By implication, I will have -1 to be multiplied by +6, and that gives us -6. So summing everything up, we're going to have +6, which makes the reactant side to be equals to the product side. And with that, we have balanced atomically and ionically. This will make our equation 1. For the oxidation half cell equation, we have SO2 to give SO4 2 minus aqueous. Now, to balance atomically, note that we have 1 atom of sulfur, and at the product side we have 1 atom of sulfur. But here we have 2 atoms of oxygen, and at the product side we have 4 atoms of oxygen. So there is a difference in the number of atoms of oxygen present. So we have to simply increase the number of oxygen at the reactant side by 2 to match up with the number of oxygen at the product side. Hence, we have plus H2O. Now, how many atoms of oxygen do we need to add to the reactant side? We need 2 atoms of oxygen. Hence, I did this place to be 2 oxygen atoms. But by implication, we would have 4 atoms of hydrogen introduced already. Hence, we have to introduce 4 atoms of hydrogen ion. Take note of the fact that we balance an ionic oxygen or oxygen in its combined state carrying charge with an ionic hydrogen. That idea between the negative charge and the positive charge is bringing to your notice a kind of electrostatic relationship that might occur between oxygen and hydrogen to form molecules of water, as you have at the reactant side. Now let's check. We have in SO2 we have 1 atom of sulfur and 2 atoms of oxygen. In 2H2O we have 4 atoms of hydrogen plus 2 atoms of oxygen. For the product side, in SO4 we have 1 atom of sulfur and 4 atoms of oxygen, and then we have 4 atoms of hydrogen. So it means it is balanced. This is equals to 4. So atomically the oxidation half cell equation is balanced. Now let's check it ionically. SO2 has no charge, hence the charge is equals to 0. So we have 0. H2O has no charge, hence the charge is 0. We have 0. Then SO4 2 minus. The charge here is 2 minus times 1, that gives you -2. The charge here is plus 1, invisibly 1, times 4, that gives you plus 4. In total, we have plus 2 at the product side. So what we have to do is either to reduce this back to 0 or to increase this to plus 2. For this example, I would like to increase it to plus 2. Hence, we have -2e minus. As you know, -1 times -2, which is the coefficient of the electron, will give you plus 2. And so, we've increased that to plus 2. Now the charges are equal, plus 2 plus 2. Hence, this becomes our equation 2. The next thing to do is to ensure the coefficient of the electrons for equation 1 and 2 are equal. So to do that, multiply equation 1 by the coefficient of electron in equation 2, that is, multiply by 2, and then multiply equation 2 by the coefficient of electron in equation 1, which is by 6. Now, note that the aim of multiplying equation 1 by 2 is to ensure that this electron goes to 12, right? And multiplying equation 2 by 6 is to ensure that this number of electrons goes to 12, so as to cancel out the 2 electrons in the end. But another way of doing this is to multiply equation 1 by 1 and multiply equation 2 by 3. Multiplying equation 1 by 1 would leave this electron unchanged, and multiplying equation 2 by 3 would increase this electron to 6, which is still the same goal, and the goal is to cancel out the 2 electrons. So whichever way you go, as a student, you are still on the right track. So I'll be going by the first method, which is multiplying the equations by the coefficient of their electrons, and in the end I will try to cut out the excess values. So we are multiplying equation 1 by 2, and that gives us 2Cr2O7 2 minus plus 28 moles of hydrogen ion plus 12 moles of electron to give 4 moles of chromium ion plus 14 moles of H2O. This gives our equation 3. Then for equation 2, we have 6 moles of SO2 plus 12 moles of H2O minus 12 moles of electron to give 6 moles of SO4 2 minus plus 24 moles of hydrogen ion. This gives our equation 4. So the next thing to do is to get the next equation by adding equation 4 to equation 3. So to add, you are considering the reactant part of each of those equations to be added together, and so we have 2Cr2O7 2 minus plus 28 moles of hydrogen ion plus 12 moles of electron plus 6 moles of SO2 plus 12 moles of H2O minus 12 moles of electron to give 4 moles of chromium ion plus 14 moles of H2O plus 6 moles of SO4 2 minus plus 24 moles of hydrogen ion. Now observe that we can cancel out the number of electrons because we have plus and minus 12E. Then take note of this 28 moles of hydrogen ion and 24 moles of hydrogen ion. We can subtract the two by either assuming we are bringing this to the product side or we are taking this to the reactant side. While taking it to the reactant side, the sign changes from positive to negative. Going by that, we can cancel out this, then cancel out this, so it remains 4 moles of hydrogen ion here. Also, take note of 12 moles of water and 14 moles of water. We can take it out, so it remains 2 moles of H2O, and this is out totally. In total, we'll be left with 2 moles of Cr2O7 2 minus plus 4 moles of H plus 6 moles of SO2 to give 4 moles of chromium ion plus 2 moles of H2O plus 6 moles of SO4 2 minus. Now the last thing to do is to check out for a common factor that could divide the coefficient of the species at the reactant side and at the product side without a remainder. So I have 2 divided by this, 2 divides this, 2 divides this, 2 divides this, and the last. So we have 3 remaining here. This is out. This gives you 2. This gives you 3. This gives you 2. And this is out of it. In the end, I'll be left with Cr2O7 2 minus plus 2H plus 3 moles of SO2 to give 2 moles of Cr3 plus H2O plus 3 moles of SO4 2 minus. Now let's check ionically. We have 2 minus here, 2 plus or plus 2, 0 plus 6, 0 minus 6. And minus 6 plus 6 gives us 0. Plus 2 minus 2 or 2 minus gives us 0. It means that ionically it is balanced. Now let's check it atomically. We have 2 atoms of chromium here. We have 2 atoms of chromium. We have 7 oxygen plus this number of oxygen. That's 6 plus 7. That gives you 13. So we have 3 times 4 here, which gives you 12 oxygen plus the last one here. That gives you 13 atoms of oxygen. That's correct. 2 atoms of hydrogen. Here we have 2 atoms of hydrogen, which is correct. Then we have 3 atoms of sulfur, and lastly we have 3 atoms of sulfur. It means that it is atomically balanced. Now the last thing I'll be talking talking about is what makes this equation acidic, and it is just the presence of hydrogen ion. So whenever I balance redox equation in an acidic medium, H plus must be present not in the combined state but in the free state, whether at the reactant side or at the product side. But it cannot be both at the reactant side and at the product side. It must be either at the reactant side or at the product side. That confirms that you have balanced the equation in an acidic medium. Thank you for making me a part of today. Have a nice day.